Hello everyone, I am Akhilesh Kumar Srivastava from ABS Engineering College, Ghaziabad. In the series of the operating system lectures, we were discussing about the mass storage management. In the previous two turns, we have discussed about the structure of the hard disk and how the disk arm moves in the case of the hard disk. And we have seen that how can the operating system control the movement of the disk arm. This actually is known as the disk scheduling algorithm, means the operating system can apply any of the available algorithms for controlling the disk arm movement. In today's lecture, we will see some of the numerical related to the disk scheduling algorithm. So, the outline of the lecture will be that we will see the disk scheduling algorithms, we will just see the summary and then we will solve the numericals, and finally, we will discuss about how can we select the disk scheduling algorithm. So, these are the algorithms that we have discussed on the last turn. We have seen that the disk arm can be controlled by the operating system with any of these algorithms, the FCFS, SSTF, scan, C-scan, look and C-scan. So, the FCFS says that wherever the disk arm is currently, it goes and satisfy the request which has come first. It goes and satisfy the request which has come next and so on and so forth. In the case of the SSTF, wherever currently the disk arm is, it finds out the request which is least apart from the given distance or current location, or it finds out the request which is nearest one to the current disk location, current head location. In the scan algorithm, more like the elevator algorithm, the disk arm moves from the lowest number of tracks to the highest number of track and satisfying the request, and then it comes from highest number of track to the lowest number of track and it satisfies the request. So, while going up it satisfies the request, and while coming down it satisfies the request. In the C-scan algorithm, while going up we satisfy the request, but while going down we do not satisfy the request. So, if this is the lowest track number and this is the highest track number, so the movement will be from the lowest track number to the highest track number, satisfying the request, and then from coming down from the highest track number to the lowest track number, the requests are not satisfied. After this, we have seen the look algorithm, which is actually the variation of the elevator algorithm. In the look algorithm, the travel is a bit restricted, like we move from the minimum request to the highest request number, and then while coming down we go from highest request number to the lowest request number. While going up we satisfy the request, and while coming down we satisfy the request. Similarly, in the C-look algorithm, which is actually the variation of the C-scan algorithm, while going up from the minimum request to the highest request, we satisfy the request. Then we come down to highest request to the lowest request while not satisfying the request, means while coming down we do not satisfy the request, and then we again go up and satisfy the request. So, the travel is restricted, or the movement of the head is restricted to the highest number of the request and the lowest number of request, but while moving up or while going up we satisfy the request, but while moving down we do not satisfy the request. So, depending on this we will see some of the numericals. First, take this numerical. This is saying that the disk with 200 tracks, usually when the disk is given and the tracks are specified, we number the track from 0. So, the minimum track number will be 0 and highest track number will be 199. The queue has a random request from the different process in the order this 55, 58, 39, 18, 90, 160, 150, 38 and 184. Initially the disk arm is at 100. Using the FIFO, SSTF scan and C-scan algorithm, you have to find out the movements. So, it is very simple to find out. We already have discussed this, that you have to just arrange these requests on the timing diagram or the Gantt chart. So, the minimum request is 18, so it will come here. The next request will be 38, the next request will be 39, the next request will be 55, next request will be 58, somewhere in between we have to locate 100 also, so that we can start the movement from there. And then we have a request number 90, so just let us mark so that we can think of that we have completed these requests. So, the next request is 150, next is 160 and one is 184. So, these are the requests and we have numbered this, and we have to find out the current location of the disk arm, which is at 100. So, the movement will start at 100. So, the first come first serve algorithm or first in first serve algorithm will have a movement according to the order that we are seeing here. 55 will be the first one to serve, and then from 55 we will move to 58, and then from 58 we will move to 39, I am sorry, 39, and then from 39 I will move to 18, and then from 18 I will move to 90, and then from 90 I will move to 160 while satisfying the request, and from 160 I will move to 150 for satisfying the request, and then from 150 I will move to 38 for satisfying the request, and then from 38 to 184 for satisfying the request. So, this is the order in which the requests are satisfied according to the first come first serve scheme. If we apply this scheme on the SSTF algorithm or according to the SSTF algorithm, so then we will have to find out the movement. For example, if this is the 100 track number and this is the current location of the read write head. So, out of the request we will have to find out which is the nearest request. So, the nearest request according to 100 will be either 90 or on the right side 150. So, out of 90 and 150, 90 is the nearest one. So, from 100 I will move to 90. Okay, then we will have to find out which request is nearest to 90. So, there are two possibilities. From 90 you can move to 58, or you can from 90 you can move to 150 on the right hand side. So, 58 is the nearest one. So, obviously, you will satisfy the request number 58. Similarly, from 58 the nearest request is 55. So, you satisfy that request. From 55 the nearest request will be 39. So, you satisfy that request. From 39 the nearest request will be 38, you satisfy that request. From 38 the nearest request will be 18, you satisfy that as well. There is no space, just pardon me for this. So, from 18 the nearest request will be obviously on the right hand side, obviously 160, 150 and 184. The nearest one is 150. So, you go to 150 and satisfy that request, and then from 150 160 will be the next request, and then from 160 you go to 184 and satisfy the request. So, this is the way we do it with the SSTF algorithm. Similarly, in the case of the scan or the elevator algorithm, what we will do, in the scan we are moving up and satisfying the request. We will have to consider that where this is moving. So, it just take this as the disk arm is moving up. So, when it is moving up, it will satisfy the request. So, it will go from 100 to the last track number, which is 199, and then from 199 it will go to the lowest track numbers. But yes, in between 100 and 199 the request will come 150, 160 and 184. It will satisfy all those requests, and when it is moving down it will satisfy the request 90, 58, 38, 39, 38 and 18. Since we do not have more requests, so it will, or our computations will stop at 18. So, this is according to the scan algorithm. When it is moving up, it is satisfying the request, and when it is moving down, it is also satisfying the request. What will happen in the case of the C scan? In the C scan, just looking here itself, from 100 it will go to 199 and will satisfy the request. From 199 it will go down to 0 and will satisfy the request. So, sorry, it will not satisfy the request, and then from 0 it will once again move up to 90 and will satisfy all the requests which are coming in between. Okay. So, from 100 to 199, from 199 to 0, and then from 0 to 90 for satisfying the request. So, this is according to the C scan algorithm. Let us take another numerical. What it is saying that there is a disk and which has 4 platters. 4 platters means there will be surfaces as 0, 1, 2, 3, 4, 5, 6, 7. There will be 8 surfaces total, and there are 200 cylinders which are numbered from 0 to 199. On each of the track there are 256 sectors, and these sectors are numbered as 0 to 255. The following 6 requests come in the form of sector number, cylinder number and platter number. So, we are more interested in the track. So, track is actually the cylinder number only. So, we are only interested in the cylinder number. are received by the disk controller at the same time. So, we have 72 of our interest, 134, 20, 86, 116 and 16. So, these are the quantities of our interest. Now, currently the head is positioned at sector number 100 of cylinder number 80. So, once again the cylinder number 80 is the desired one. So, 80 is the current location of the read write head. It is moving towards the higher cylinder. So, its movement will be on the right, and the average power dissipation in moving the head over 100 cylinder is 20 milliwatts. So, for moving to 100 cylinder 20 milliwatt. So, what will be for movement of 1? So, that will be 20 by 100. So, 0.2 milliwatt is actually consumed for the movement of one cylinder. And for reversing the direction of the head, the movement, if it is moving up and then it has to decide that it has to come back or it has to move back. For moving back, the power consumption is 15 milliwatts. So, power dissipation associated with the rotational latency is 0 or negligible. So, what we have to find? We have to apply the shortest seek time algorithm, and we have to find out how much is the total power consumption. So, we will have to find out the total movement, and then we will have to multiply with the amount of power dissipated for movement of the heads. Fine. So, currently the location is 80, the request which are coming is 134, 20, let us mark this somewhere. So, 20, 86, 72, 116 and 16. So, 16 is the smallest request, and then 20, and then 72, it will come towards the left, and then 86 on the right of 80, and then 116 on the right of 80, and then 134 on the right of 18. So, 80 is the current location. So, with the SSTF algorithm, you can see that there are two possibilities for this disk read write head. From 80, either it should go to 86 or 72. So, 72 is 8 distance apart and 86 is 6 distance apart. So, we should select to go to the 86. It was moving up, fine, it is moving up only. It has satisfied the 86 request number. From 86, there are two possibilities, either to go to 116 or 72. So, if you go to 116, 30 distance will be travelled. If the disk arm is moved from 86 to 12, 14 distance will be travelled. So, you change the direction and go to 72. So, the one change of direction has taken place here. And then from 72, there are two possibilities, either we should move to 20 or 116. So, obviously, we will move to 116. From 116, there is only one possibility, to go to 134, because it is 22 distance or 18 distance apart. Rest of the requests are very far. So, from 134 you go to 20 satisfying the request, and from 20 you go to 16 while satisfying the request. So, this is the map that we have prepared, that what will be the path. Now, let us find out what is the total distance the disk arm has moved. From 80 to 86 it is 6, from 86 to 72 it is 14, from 72 to 116 it has taken 28 plus 16, 44 distance. Okay. From 116 to 134 it is 18, and then from 134 to 20 and then to 16. So, we can simply subtract 134 minus 16. So, this will be 118. Okay. If you sum all these, you will find 20, 64, 82 plus 118. So, this is 200. So, total number of movements which has taken place is 200. So, how much power is dissipated for one movement? It is 0.2. So, if you multiply this with 0.2, this will actually be 40. So, 40 milliwatt is spent for movement, and then for reversing the direction we require 15 milliwatt. So, from here it has changed the direction once. So, one change is here, another change is here, another change will be here. So, 3 times the direction has been changed. Once again I explain, from 80 to 86 no problem in the same direction, but from 86 to 72 it has changed the direction, from 72 to 116 it has changed the direction, from 134 to 20 it has changed the direction. So, direction was changed 3 times. So, 3 into 15. So, total if you sum all these will be 85. So, 85 milliwatt power is consumed for doing this travel. Now, let us take another example. It is saying that the disk requests are received by a disk drive for cylinder 5, 25, 18, 3, 39, 8 and 35 in that order, means it is coming in this order only. A seek takes 5 milliseconds. Seek means you have to locate to the desired track. So, the disk arm has to move. So, this is the seek time. So, it is said that the seek time is 5 millisecond per cylinder moved. Then how much seek time is left, or how much seek time is needed to serve these requests for shortest seek time first algorithm. So, once again we have to find out the we have to apply the SSTF algorithm for solving this question. So, currently it is said that the disk arm is at 20. So, before 20 there will be request 5, 3, 8. So, let us mark this 3, 5, 8 and after this the request will be 20. After 20, 18 is also there. So, let us mark 18 as well. After this 20 which is the current location. After 20 it will be 25 and 35 and 39. So, according to the shortest seek time algorithm, from 20 we will move to 18. It is 2 distance apart. From 18 there are 2 possibilities, either to go to 8 or 25. So, I will prefer to go to 25 because this is 7 distance apart. So, you can do the simultaneous computations also, 2 and then 7 movements that took place. From 25 obviously 35 is the nearest one. So, go to 10 distance for 35 and then from 35 you can move to 39 travelling 4 distance. From 39 you have to go down to 8. So, 31 distance actually has been taking place and then from 8 to 5 3 distance, then from 5 to 3 2 distance. So, if you add all these 9, 19, 23, 28 and 39, 31. So, this is 59. So, 59 is the total movement which has taken place, and how much is the power consumed or how much is the time taken? So, it is 5 millisecond. So, if you multiply this with 5 millisecond, so this comes out to 295 millisecond. So, this is the answer for this question. Let us solve another one. This is saying that there are 16 surfaces, 128 tracks per surface, 256 sectors per track and 512 bytes of data are stored in bit serial manner. The capacity of the disk pack and the number of bits required to specify a particular sector in the disk respectively are. So, here it is said that the 16 surfaces are there, 128 tracks are there and 256 sectors are there. So, you multiply number of surfaces with the number of tracks per surface with the number of sectors per track. So, these are the total number of sectors. These are the total number of sectors. Now, how much will be the disk capacity when you multiply this with the capacity of each sector, which is 512 bytes, then you will get the answer. So, this it will be 2 raised to the power 4, 2 raised to the power 7, 2 raised to the power 8 into 2 raised to the power 9. So, 9, 8, 17, 24, 28. So, this is the disk capacity 2 raised to the power 28. So, 2 raised to the power 28 can be set to 256 megabyte. So, the disk capacity is 256 megabyte. So, either we have this answer or we have this answer. Now, see the next question which is asked that the capacity of this pack which has been given and the number of bits required to specify a particular sector on the disk. So, for specifying a sector you will have to find out how many total sectors are there. So, you can see that the total number of sectors are this, we already have found. So, if you represent this in the powers of 2, so this will be equals to 2 raised to the power 19. Okay. So, 19 is the number of bits to represent to any of the sector, or to refer to any of the sector we require 19 bits. So, A is the correct answer. Then let us take this question. This is actually the theoretical question that you have to answer according to the logic that you have built. In this scheduling algorithm, the disk head moves from one end to the another end, serving the request along the way. When the head reaches to the other end, it immediately returns to the beginning of the disk without serving the request on the return trip. So, the options are look, scan, see look and see scan. It looks like that it is returning and not satisfying the request. So, either it will be see look or see scan. We will have to relook at the question once again to select one of see look or the see scan algorithm. So, it is saying that it moves from one end to the other end, meaning that one end to the other end, from the extreme one end to the extreme higher end, and it is satisfying the request. So, obviously, it will be the see scan algorithm. In case it is satisfying only the request up to the maximum request number, then it will be the see look algorithm. Let us take another question. It is saying that if the disk head is located initially at track number 32, so 32 is the current location, find the number of disk movement required with the FCFS scheme if the requests are these. So, you can simply satisfy this or solve this question, because this is a very simple one. So, the first request which is coming is 98. So, let us mark it here. So, 14 is the first request, and then after this 37, then 65, 67, 98 and 124. It is going after this, please pardon me for this. So, from 32 I will first go to 98, and then from 98 I will go to 37. From 37 I will go to 14. From 14 I will go to 124. From 124 I will go to 65, and then I will go to 67. So, this will be the order, and you can simply sum this and find out the answer. Let us take another one. It is actually asking you to find out the disk movement with the SSTF scheme. So, the disk arm disk has 100 cylinders, meaning that you will have 100 tracks, and usually we number them from 0 to 99. The disk requests come for the cylinders 12, 26, 24, 4, 42, 8, 50 in that order. The driver is currently serving a request at cylinder number 24. So, 24 is the current location. A seek takes 6 milliseconds per cylinder moved. How much seek time is needed for shortest seek time algorithm? So, we will first have to find out the number of the movements, and then the total number of movements will be multiplied with the time taken for movement of one cylinder or one track. So, let us find out the movements. So, the requests are, you can mark it here, 4, 8, 12, 26, 42 and 50. Let us count the number of the requests which are there: 12, 26, 24, 4, 42, 8 and 50. So, there are 7 and we have marked them 7. Currently, the disk arm is at 24 and one of the requests is also 24. So, obviously, it will take no time to satisfy the request as 25. So, it does not have to move and satisfy the request 24. From 24, it will move to the nearest one. So, it will obviously move to 26, which is a 2 distance apart. So, from 26 it has 2 options, either to go to 46 or 12. So, 12 seems to be the nearest one. So, it is 14. So, from 12 it will move to 8 because it is the nearest one. From 8 it will move to 4 because it is the nearest one at a distance of 4, and then from 4 it will move to 42 to satisfy the request. It has to travel 38 distance, and from 42 to 50 requiring 8 distance. If you sum all these, this will be the total number of the movements. So, this comes out to 56 plus 14 means 70 movements. So, when you will multiply this with the time taken for one movement, which is 6 milliseconds, so this will be 420, and if you convert, this is the millisecond, if you convert this to the seconds, this answer will come out to 0.42. Now, the next one, this is saying that this is a logical question. Consider the following 5 disk access request for the in the form of request ID, cylinder number. So, P is the request ID and 155 is the cylinder number. These that are present in the disk scheduler Q at the given time. Assume the head is positioned at cylinder number 100. So, 100 is the current location, and it follows the shortest seek time first algorithm for serving the request, and we have to find out which of these is true. So, since this is asked with respect to the PQRST, so let us do it with the help of this only. So, the requests are 155, 85, 110, 30, 115. So, 30 is a request which is S, and then 85 is a request which is Q, and then 110 is a request which is R, then 115 is a request which is T, and finally we have P request with 155. So, shortest seek time algorithm, currently the disk arm is at 100. So, 110 will be nearest one, and then from 110, 115 is the nearest one. Then from 115, two options are there, either to move to Q or P. So, obviously Q is nearest one, so I will satisfy that. And then from 85, S is the nearest one, and then from here we have P to satisfy. So, now if you see that the questions which is asked, let us verify them one by one. T is serviced before P. So, T is here and P is here. So, T is not serviced before P. Yes, T is serviced before P. So, this is correct. T is served here and P will be served later to this. Then Q is serviced after S. So, S is serviced here and Q is serviced here. So, Q is serviced first and then S is serviced. But here it is what it is said that Q is serviced after S. So, this is wrong. And then finally, it is saying that the head reverses the direction of movement between servicing Q and P. Obviously, it is changing the direction between Q and P. So, this is true. And R is serviced before P. Yes, R is serviced before P. R is the first one which is serviced and P is the last one which is serviced. So, this is also true. So, only wrong option is B. Similarly, you can solve all those problems which is related to the disk scheduling. This is very easy to solve. You just have to remember what is the logic behind the various disk scheduling algorithms. So, there are more questions that you can solve. When you are selecting the disk scheduling algorithm, you have to keep some of the things in the mind. You see what is the requirement. If the requirement is, if you can find out the shortest distance in a very efficient manner, then you should go to the SSTF algorithm. When all the requests are at the track number 0, then CLOOK algorithm or C-scan algorithm will be the best one. Fine. In case you do not have to go to the minimum number of the track to find out the various requests, then the CLOOK algorithm will be the good one. So, according to the requirements, you will be selecting a disk scheduling algorithm. So, thank you for today's lecture.